Hey folks, Ms. Gosling here. In this video, you're going to learn about centripetal acceleration. By the end of the video, you'll be able to find the centripetal acceleration of any given object. So let's go ahead and start by talking about what centripetal acceleration is. So you'll notice in the last video, I was talking about angular speed and linear speed, not linear and angular velocity, because I don't have a constant linear velocity. That is, my linear speed might be constant. That is, I might be going, for example, at 10 meters per second around the circle, but my direction is constantly changing. And so since my direction is constantly changing, that means that there must be some kind of acceleration. And we call that acceleration centripetal acceleration, which just means towards the center. So the centripetal acceleration is always going to point directly to the center of the circle. So I'm on top of the circle, it'll point down. If I'm over here on the right, we'll be pointing in towards the left side of the circle, and so on and so forth. Let me go ahead and fix this angle here. I'm going to draw a couple more centripetal accelerations so y'all can all see what that looks like. And if I was to draw my centripetal acceleration at a random point on the circle here, again, it will always point in. So the other thing I want to mention, because we didn't actually talk about what linear speed looks like on a circle, but my linear speed is always going to be perpendicular to my centripetal acceleration, like so. Now in this case, I am moving clockwise around the circle. If I was moving counterclockwise, I could do the same thing, but I would draw my linear speeds like that. So let's go ahead and draw in some of those arrows. And I'm going to also really quickly just label these as going clockwise and my yellow arrows as going counterclockwise. So that's kind of our basic using vectors to represent our tangential velocity this time, right? Because we are looking at the direction as it changes, and our centripetal acceleration. So we can actually find our centripetal acceleration using our linear speed. So our acceleration is our linear speed squared divided by our radius. Now, 99.9% of the time, this is what you'll be using. You'll be looking at linear speed and radius to find acceleration. However, sometimes you may be asked to use your angular speed to find your acceleration instead. So in that case, what we're going to need to remember is that my angular speed omega is equal to v over r. Therefore, my linear speed is equal to omega times r. If I were to plug that into this equation here, what I would get is that my acceleration is equal to v squared over r, or omega r squared over r. If I distribute that squared, that exponent, I get omega squared r squared over r as my acceleration. Thus, my acceleration, my centripetal acceleration, which I usually represent as a sub c, is given by omega squared r. So again, 99.9% of the time, you will have your linear speed. You'll use that to find your centripetal acceleration. But 1% of the time where you do have your angular speed instead, you can use this equation here to find our centripetal acceleration as well. So with that, let's go ahead and look at an example. A photon moves at the speed of light, 3 times 10 to the 8th meters per second, on a path of radius 3 nanometers. What is its acceleration? So let's go ahead and start by drawing a picture. So here is our circular path and our photon moving around it at a speed of 3 times 10 to the 8th meters per second. And that path has a radius of 3 times 10 to the negative 9th meters, or 3 nanometers. So that means that I'm ready to go through my guess method. So let's start by listing my givens. So I know that my linear speed v is 3 times 10 to the 8th meters per second. And I know that this is linear in part because it's given in meters per second, not radians per second. I also know that I am traveling on a path of radius 3 nanometers, which is 3 times 10 to the negative 9th meters. If you did not know this immediately, your metric prefixes are in the data booklet, but you also probably want to practice with them a little bit to make sure you can do this quickly. And that brings us to from our given to our unknown. And our unknown is going to be our centripetal acceleration. So because we have our linear speed, not our angular speed, what we will say then is that our centripetal acceleration is equal to v squared over r. Therefore, when we sub and solve, we will find that our centripetal acceleration is given by 3 times 10 to the 8th squared over 3 times 10 to the negative 9th. And when I throw that on a calculator, I get that my centripetal acceleration is 3 times 10 to the 25th meters per second squared. And there you have it. Let's look at one more example though. Ms. Trunchbull is practicing her hammer throw and swings her hammer around 8 times in 2 seconds before releasing it. The hammer has a length of 3 meters and a mass of 5 kilograms. What is the hammer's centripetal acceleration? So let's go ahead and take a look. So we know that Miss Trunchbull is swinging this hammer around. Let's go ahead and make this a little bit bigger. She is swinging her hammer around, and that hammer makes 8 revolutions in 2 seconds. So that means it's going through 16 pi radians in 2 seconds. And I know this because 1 revolution is equal to 2 pi radians, just by definition, how we define the radian. So I also know that my hammer has a length of 3 meters, so that will be my radius r. And I'm going to go ahead now and go through my guess method. So I know that that I'm going through 8 revolutions in 2 seconds, so that omega, my angular speed, is 16 pi radians over 2 seconds, or 8 pi radians per second. And I know that r is equal to 3 meters, which means that I'm now ready to list out my unknown, which is, again, my centripetal acceleration, a sub c. So now that I have that, I can use my equation. And in this case, or I can write my equation down. And in this case, since I have omega, I want to use my second equation for my centripetal acceleration. A sub c is equal to omega squared times r. And I don't have to do any shuffling around since my centripetal acceleration is already by itself, which means I'm ready to sub and solve. And I will say that a sub c, my centripetal acceleration, is equal to omega squared times r, or 8 pi squared times my radius of 3 meters. Thus, my centripetal acceleration is approximately 1900 meters per second squared. And there you have it. Here is our centripetal acceleration for this problem using a slightly different method to solve. So with that, let's go ahead and talk takeaways. First of all, objects in circular motion are always accelerating, even though their speed is constant. And secondly, an object's centripetal acceleration is equal to its linear speed squared divided by the radius of its circular path. It's also equal to, of course, omega squared times r. So with that, you now know all about our circular kinematics. It's your turn to try some problems on your own. Best of luck and happy solving.